Picture yourself on a peaceful hill, observing the sky explode into a kaleidoscope of colors as the sun rises above the horizon. It's a daily wonder that most of us overlook, the golden tones of orange, red, and pink sweeping across the sky. But this stunning sunrise is merely the last page in the long journey of light. If we follow the course of these photons from their termination in your retina at the rear of your eye, through the atmosphere of Earth, through the 150 million kilometer expanse between our world and its parent sun, and then through the diverse and violent layers of that star, we find the origin of the heat on your face and the colors splashed across the sky. The core of the sun, a nuclear furnace that has been burning for 4.5 billion years, formed in a cosmic cradle from the debris of bygone stars. The radiant ball of burning plasma that fills our horizon is the result of intricate forces that have unfolded over thousands of years. But just how much do we understand about such a central aspect of our existence? What are the mechanisms that control its massive energy? What are its most spectacular aspects? And how are scientists probing its depths to unravel its secrets? And you're watching Astronomy. Come with me in this supercut as we descend into the depths of our sun and find out what lies beyond the blinding veil of light and time. Where to begin? Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory, or SDO, a NASA spaceflight deployed in February 2010. SDO sought to more fully comprehend the solar variations that affect life on our planet and our technological infrastructure by examining the dynamic solar surface and atmosphere at various electromagnetic wavelengths. By observing light outside the visible range, NASA was able to distinguish out usually invisible information important to our comprehension of the sun. We photographed this with a 19.3 nanometer wavelength, which is light present in the extreme ultraviolet range. On a wavelength equivalent to a 1 million Kelvin color temperature, we can easily observe the upper region of the sun's corona. Interestingly enough, the sun's corona is also visible to the naked eye from time to time, such as during a total solar eclipse. When the moon is in its correct position between the Earth and the sun for a very brief time, the appearance of the central brighter disk, the photosphere, is completely obscured, showing a glowing outside. Although this is an awesome sight already, the corona is still far from as detailed as it appears in this photo captured by the SDO. This makes it a valuable tool for scientists' research. But let's dig a bit deeper, to features of the sun just below the corona. At a color temperature of 20 million Kelvin, the very strongly colored spots show up to mark events known as solar flares. Here is some imagery of a particularly hectic week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They are colossal explosions, where the sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the sun itself, from which the fields actually stem. Solar flares and coronal mass ejections. Both are very energetic events, on the order of millions of nuclear bombs all at once. The magnetic reconnection processes that lead to them can release enormous amounts of radiation, in the case of solar flares, and material into and out of the sun. For coronal mass ejections, millions of tons of charged material even thousands of kilometers per second. But they are not the sole characteristic of the sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the sun, are another fascinating feature, which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma, which are magnetically open, meaning that, rather than forming closed loops that go back to the sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with the Earth's magnetosphere, beautiful aurora lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the sun's outer layers. Non-visible spectrum light is such a powerful tool, And there are so many various features in the outer layers of the sun to examine. There are solar filaments, the huge loops of plasma that project from the sun's surface. These gigantic loops are huge enough to make the Earth appear as a small speck and can stretch hundreds of thousands of kilometers into space. They can develop in as short a time as a day, but a stable prominence can remain in the corona for months. In this case, we observe as a prominence snakes its way out of the photosphere and into the sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly. The sun's intense magnetic fields are causing this material to move. One thing you may not know about the atmosphere of the sun is that rain sometimes falls there. Not all of the charged plasma shot into the sun's corona escapes out into the solar system. Some is left in the corona, trapped and cooled, before falling back onto the sun as a shining rain. This coronal rain is pretty to see, but is best viewed from afar. It's still millions of degrees in temperature. Of course, gently falling back towards the sun's surface is only the destination of some of the sun's plasma. This is where the analogy to Earth fails. After all, clouds on Earth do not crack like a released elastic band shooting into space. On the sun, owing to tightly wound magnetic fields, they do. This is a time-lapse of a coronal mass ejection. See how the structure builds at the bottom left of the sun for some time, before ultimately breaking and propelling billions of tons of plasma out into the solar system. Even with the Earth's magnetic field, being struck by a strong one of them could end up being disastrous for our satellites and power grids. All of these structures are captured by the SDO here using a 30 nanometer wave of light, which is equivalent to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is crucial when attempting to image these features, since they occur more frequently in some years than in others. Indeed, each structure is reliant on the sun's solar activity, switching between an 11-year solar cycle. But about that later. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the sun's corona. Taken over the same period of time, the next two images are taken with different wavelengths of light. The first, taken at a color temperature of 600,000 Kelvin, shows the peaceful corona and has coronal loops. The second, taken at a color temperature of 2 million Kelvin, shows the far hotter active areas of the corona. The dramatic contrast between the two pictures serves to emphasize the value of employing varied methods when examining the star. A single, isolated solar event might be what an event seems to be at first glance, but it can instead shown to be a convoluted, interconnected series of events. And we have not even technically traversed the sun's atmosphere yet. Proceeding further inward, let's examine another image taken by the SDO using a 160 nanometer wavelength of light, period of the transition region. The transition region is a layer that sits between the sun's corona and the chromosphere, the lowest layer of the sun's atmosphere. It's very thin layer, about 100 kilometers thick. In this region, the thermal temperature of the sun ascends spectacularly from about 8,000 to 500,000 Kelvin. To put this into perspective for an earthling, blazingly hot lava, spewing out of Hawaii's 1170 degrees Celsius, or 1,143 Kelvin. The temperature at the lower inner end of the transition region is nearly 6 times hotter than this one. At the top end of the transition region, the temperature is over 346 times hotter. Traveling further inward, we are submerged in the sun's chromosphere, the final layer of atmosphere before we actually hit the sun's surface itself. Captured here on 170 nanometer ultraviolet light, it is calculated to be around 1,700 kilometers thick. Studying the chromosphere closely, we find some fascinating features referred to as spicules. Swaying back and forth like reeds of long waving grass in the wind, these flowing jets of plasma erupt upward from the surface of the sun at velocities up to 100 kilometers per second, or about 282 times the speed of sound, and can be as long as almost 10 kilometers, more 1 kilometer higher than Mount Everest. Developing and dissolving in about 5 to 10 minutes on average, the mechanisms involved in these spicules were largely unexplored and discussed for a period, as it wasn't clear how magnetically charged particles could ever leave the magnetic fields of sun at that level. That was until 2017, when a group of scientists carrying out an extremely detailed model of the spicules found that their source must be connected with neutral particles. Scientists did not initially include neutral particles in their models of the Sun since they did not believe that they impacted the movement of the magnetically charged particles, but after adding them, it turned out that the neutral particles provided the magnetically charged particles with unexpected buoyancy that they required to leave the Sun's plasma and shoot upwards into spicules. Going lower down through the Sun's lower atmosphere, we finally arrive at the photosphere, the face of the Sun itself, which is best photographed with visible light. Although the boundary of the photosphere seems definite and sharp, as it usually does to our unaided eye, this is merely due to how far away the Sun is. The Sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid, or gas state in any region of the Sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a solid fixed boundary of the Sun, as the picture might give you to believe, and unfortunately, it is the star's deepest layer which can be measured directly by scientists. And if you look more closely, you might see some dark spots on the left side. They are called sunspots, and show darker than the rest of the photosphere, since they are colder, but that's only against the background of their blazing hot surroundings. Sunspots, unlike coronal holes, occur in regions where magnetic fields are especially strong. Here, heat gets stuck underneath the photosphere because of reduced convection in these regions. In comparing this photo of the Sun to an earlier one snapped with the aid of extreme ultraviolet light during the same time, there is a relationship between sunspots and solar flares. The interesting solar flares and sunspots occur in the same place. Having looked beneath the surface, it is obvious that one has to be the cause of the other. Sunspots range in size from 15 km to 160,000 km, several times the Earth's size. Let's now take a closer look at some comparable sunspots. This photograph was captured using the Swedish Solar Telescope, which is located here on Earth, and employing a wavelength of visible light of about 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath. Lighter regions within each granule are fluid of impossibly hot temperatures moving from inside the Sun's outer interior layer to the surface. When it arrives at this edge, there is nowhere for the fluid to go but outwards and across. Once cooled slowly, the fluid flows back inwards through the dark, jagged boundaries around each cell, before doing it all again, the cycle. The process is very similar to the convection currents of the Earth's mantle, which drive plate tectonics. This process isn't a laughing matter. Although on average it's estimated that each granule exists for as short as 20 minutes, the flow in the cells attains supersonic speeds of over 7 kilometers per sonic booms. Interestingly, these granules can also be observed in the full disk image that we saw before using the same wavelength of visible light. You might have thought that this picture looks very grainy for one of these high-tech space probes. And you're correct, it is. But that graininess is the granules on the Sun's photosphere, and not an effect of processing or image noise. And that's it. Unfortunately, this is as far as our tour goes, because scientists have not yet discovered how to image deeper into the Sun, either with visible or non-visible light. Much of what exists beyond this layer is shrouded in mystery, but we can glimpse the advantages of applying light of all spectrums to our research on the Sun. The Sun is teeming with vibrant activity, and so much of it would be invisible to us if not for these imaging methods. There is so much we don't know beyond this point regarding the Sun, but occasionally the secret to comprehension of something lies in the background of where it originated from. How precisely did our Sun's radiating radiance start? In order to comprehend how the Sun was formed, we need to travel back prior to our solar system even existed, around 4.6 billion years ago. Then, in a fairly tranquil part of the Milky Way galaxy, a huge cloud of gas and dust, referred to as a giant molecular cloud, moved quietly across space. It was not your run-of-the-mill cloud. It was enormous, maybe hundreds of light-years across, with a mass equal to millions of suns. In this cloud were the dispersed remains of long-dead stars that had used up their nuclear fuel long ago and had burst apart as supernovae, scattering their enriched material into space. This stellar wreckage contained a blend of elements like hydrogen and helium, the star builders, along with heavier elements such as carbon, oxygen, nitrogen, and iron. Because it contained these elements, this molecular cloud was rich soil for creating new planetary systems and stars. But such a large cloud needs a trigger to start, the cascading collapse that leads to stellar birth. Scientists suspect that this trigger may have been a shockwave from an adjacent supernova explosion, which compressed regions of the cloud, fragmenting and collapsing it into denser regions. This breakdown initiated the pre-solar nebula, the high-density region of the molecular cloud that would give rise to our solar system. Some scientists have even suggested a name for this theoretical supernova star, Coatlicue. Named for the Aztec earth and fertility goddess, Coatlicue represents the death and rebirth cycle, where in this case, the death of one star can seed the formation of new ones. As the gravitational collapse of the giant molecular cloud progressed, it did not result in a single massive object, but rather fragmented into multiple dense clumps. This fragmentation occurs due to a phenomenon known as Jeans instability, named after the British physicist Sir James Jeans. The Jeans length is an important distance in a cloud at which the strength of gravity is equated with the internal gas pressure that supports the cloud. When a specified section of cloud goes beyond the Jeans length, then it will collapse upon itself. Various regions within the molecular cloud exceed this Jeans length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse independently to form multiple protostellar cores, as opposed to one single massive body. The protostellar core was the earliest phase in our Sun's life that was recognizably star-like, collapsing into a smaller and smaller sphere by the continually clenching fist of its own gravity. The center is surrounded by infalling gas and dust. The more material that is added, the more dense and hot the core becomes, making way for the next stage of star formation, the protostar. When a protostellar core gets dense enough and hot, it turns into a protostar. The inner zone has been heated, to the extent that it starts radiating light and heat due to the energy that is released through gravitational contraction. But its center has not reached the temperatures required to ignite nuclear fusion in the core. As the protostar continues to accumulate material and grow in mass, the pressure and temperature in its core increase dramatically. Our Sun developed through this embryonic state of contraction and heating for millions of years, before eventually building up its core temperature to about 10 million degrees Celsius, at which the hydrogen nuclei started to combine into helium. And by that, the Sun was formed. During this phase, the inherent angular momentum of the material surrounding the infant star causes it to spin. A cloud of this size will always have a bit of slight rotation. Nothing in the universe is still, and conservation of angular momentum dictates that the cloud must spin faster and faster as it crunches down into tighter space, similar to how a spinning figure skater speeds up as they tuck in their arms. Around the equator of rotation, some of the material is moving fast enough to remain in orbit, but higher up and lower down the momentum is not enough to withstand protostar's hungry grasp and drops helplessly into its maw. And so the cloud spreads out into a disk, a protoplanetary disk. This disk is a cosmic lottery. As it cools and clumps together, planets, moons, asteroids, and comets will be constantly created and destroyed. Some of the material will be deprived of its momentum and fall into the Sun, while neighboring material will proceed to become one of the many bodies of our solar system today. With its new capability to fuse hydrogen atoms into helium, the Sun would finally be able to produce energy to resist the forces of gravity that were trying to compress it even more. The energy flowing out of the fusion reactions produced an outward radiation pressure that counteracted the inward gravitational force of the gas, enabling the young star to settle into a stable state called as hydrostatic equilibrium. At this point, the star no longer shrinks under its own gravity, and it takes on a stable part of its life called the main sequence. This delicate balance between pressure squeezing out and gravity collapsing in is the major axis that sets each phase of the Sun, and all stars' existence. We saw it at the first collapse, and here as it assumes a stable main sequence star, and it will be the pendulum that ultimately swings to its dramatic end. But for now, let's unpick the process of nuclear fusion, and how it's able to maintain an object as heavy as the Sun stable and firm for billions of years. To comprehend the processes of nuclear fusion in the Sun, we must look at extreme conditions existing inside its core. Current temperatures are approximately 15 million degrees Celsius and pressures greater than 250 billion times that of the Earth's atmosphere. In this fiery cauldron, hydrogen atoms lose their electrons, creating a plasma of free protons and electrons. In these extreme conditions, these protons, usually repelled by their common positive electric charges, are pushed into very close contact. The force that keeps them apart under normal circumstances is the Coulomb force, an electrostatic repulsion of positively charged particles. It's the very same force that resists as you force the same ends of a bar magnet together. Defeating this force is the main hurdle for nuclear fusion to take place. Even with the Sun's core protons having extreme kinetic energy, most collisions are still not energetic enough to surmount the Coulomb barrier. Under typical circumstances, protons require massive amounts of energy to approach one another sufficiently to be held together by the strong nuclear force. This barrier is so broad that physicists at the time of the early 1920s, employing a classical concept of how particles interact with each other, concluded that fusion should not occur at the temperatures and pressures found in the Sun's core. To solve the puzzle, we needed a scientific model that has come to explain many of the seemingly impossible phenomena that we observe in the universe: quantum mechanics. The quantum mechanics revolution of the 1920s introduced the concept of particles behaving both as particles and as waves. One of these phenomena is quantum tunneling, where particles have a certain probability of tunneling through a barrier even when they lack the classical energy needed to overcome it. In the Sun's core, quantum tunneling allows a small fraction of protons to effectively bypass the Coulomb barrier without needing to climb over it in the literal sense. Although these protons lack sufficient kinetic energy to get past the electrostatic repulsion head-on, quantum mechanics provides them with an opportunity to show up on the opposite side of the barrier. Visualize the process by looking at a diagram of the Coulomb barrier. In the diagram, you will observe a large energy barrier which symbolizes the electrostatic repulsive force between two protons at different distances. The energy required to overcome this barrier is indicated in the form of a peak. The classical physicists' calculations would put the Sun's temperature at extremely in billions of degrees Celsius, thousands and thousands of times hotter than the core of the Sun, to overcome this obstacle. But quantum mechanics permits the probability wave of a proton to tunnel through this obstacle, emerging on the other side without ever crossing over the peak. This tunneling effect is what enables fusion to occur in stars like the Sun despite the seemingly insurmountable Coulomb barrier. Once a proton has tunneled through the barrier, it gets close enough to another proton for the strong nuclear force to take over. The strong nuclear force, which is far more powerful than the Coulomb force, operates only at very short distances, on the order of femtometers, where one femtometer adds 10-15 meters, about the size of a single proton. The strong nuclear force holds the protons together, but this is merely the first step in a chain of nuclear reactions called the proton-proton chain. The proton-proton chain reaction is the primary fusion process in the Sun and other similar-sized stars, producing about 99% of the Sun's energy output. It begins with two free-range protons joining together to create deuterium, a heavy hydrogen isotope, the release of a positron and a neutrino. This process is uncommon, yet necessary, because it permits the fusion reaction to proceed. Deuterium quickly combines with a second proton to produce helium-3, emitting a high-energy photon, a gamma ray. For the last step, two helium-3 nuclei smash into each other and combine to create helium-4, emitting two protons and a large amount of energy in the form of radiation. Though the proton-proton chain is the most prevalent fusion process in the Sun, there is another process operating, more so in stars hotter and more luminous than the Sun. This process is referred to as the CNO cycle, carbon-nitrogen-oxygen for short. In the cycle, carbon, nitrogen, and oxygen nuclei act as catalysts to fuse protons into helium. The CNO cycle is more efficient at higher temperatures and contributes a small percentage of our Sun's energy output. The energy released in these fusion reactions results from a small amount of mass being converted into energy, as explained by Einstein's well-known equation, E mc2. During the fusion process, the mass of the resulting helium-4 nucleus is less than the sum of the masses of original 4 protons. This missing mass is not lost, but rather converted into energy that radiates outward from the Sun. Every second, the Sun converts about 4.3 million tons of its mass into energy. That's right, the Sun is losing mass all the time. To put this into perspective, this is equivalent of the mass of about 3 million cars being turned into pure energy every second. This is the energy that ultimately powers the Sun and provides the light and heat that reaches Earth. But before these photons, pouring out of these reactions, can reach the Earth and everything else in the solar system and elsewhere, they have to get past the 700,000 kilometers of maddening solar interior first. In order to get an idea of just how complex the Sun is, and just how it is differentiated into layers, let's trace the path of a single photon, a light particle, from its formation in a proton-proton reaction all the way to the surface. This path is far from straightforward. In fact, it will take thousands, if not hundreds of thousands, of years for this photon to complete its journey, passing through several distinct layers of the Sun, each with its own unique properties and behaviors. As we've already found out, our photon's journey starts in the core, a region that spans about 25% of the Sun's radius, but holds nearly half of its total mass. And as we've also heard, the core is incredibly dense. At around 160 grams per cubic centimeter, it's over 20 times denser than iron. To put that into perspective, if your phone was constructed out of material that dense, it would weigh as much as a heavy-duty sledgehammer. For our photon, this means the environment is so densely filled with particles that it cannot go far before it gets absorbed by a neighboring particle. Of course, not long afterwards, that particle will send the photon's bags packing and out into the chaos of the core for another particle to catch and release in some arbitrary direction. It's somewhat like trying to push one's way through a crowd of people, where every few steps you bump into somebody and need to change course. This ongoing process of absorption and re-emission is what bestows the core its chaotic character, leading to a trip for a photon that is a random walk rather than a straightforward path outward. This erratic motion of photons is akin to Brownian motion, wherein suspended particles in a fluid move about at random as a result of collisions with faster, smaller molecules. And there is no preference for the direction that a photon could fly, back out of a particle that had just absorbed it. In theory, a photon could make it all the way to the surface of the Sun before random chance directs it back towards the core. To add to the complexity, as photons are continually absorbed and re-emitted, the energy is slowly reduced from gamma rays to X-rays, and eventually visible light as they travel towards the Sun's outer layers. To understand what is happening in the core of the Sun has been a difficult task for astronomers. The core is fully obscured by the outer regions of the Sun, meaning we cannot see it directly by means of any kind of light. Instead, scientists have devised genius ways to make an educated guess about the behavior of the raging inferno beneath. One of the most important techniques is the exploration of helioseismology, the monitoring of waves passing over the Sun's surface. Just as seismologists analyze earthquakes to learn about Earth's inside, helioseismologists measure the vibrations on the Sun's surface caused by sound waves that travel through its interior. These sound waves are influenced by the temperature, density, and composition of the Sun's layers, allowing scientists to construct models of what is happening deep within. Solar neutrinos, elusive subatomic particles that I've talked about in a previous video, are also emitted during the fusion reactions within the Sun's core. Neutrinos interact so faintly with matter that they can travel directly out of the Sun in only 2 seconds, barely noticing the mess their photon counterparts are trapped in. Solar neutrino detectors on Earth have been detecting them for decades. Earth detected fewer neutrinos than would be expected according to theoretical models, causing what was referred to as the solar neutrino problem. It wasn't until scientists learned that neutrinos shift their characteristics or flavors during their travel to Earth that the enigma was solved, affirming both our knowledge of particle physics and the nuclear reactions in the core of the Sun. Then, the photon moves into the radiative zone, extending from the core boundary to approximately 70% of the Sun's radius. Here, temperatures slowly decrease from 15 million degrees to approximately 2 million degrees Celsius. The matter density also decreases, falling from approximately the density of the gold in the zone's depths to less than that of water near the surface. The prevailing energy transport process is still this frenetic process of photons skittering around in the layer, taking their energy on average towards the top. And as the plasma's density grows smaller as we go outwards, our photon has a bit more leeway, able to make larger bounds between collisions. Even here, though, beyond the center, the material of the Sun remains so dense that even a few centimeters of it might absorb as much light as many hundreds of meters of water. We can visualize such detailed models of the Sun's interior due to models such as Standard Solar Model or SSM. It is a mathematical model based on the laws of hydrostatic equilibrium, conservation of energy, and radiative transfer, basically applying our knowledge of how materials and fluids behave here in our labs on Earth to deduce the properties of a location beyond our grasp. The SSM simulates how energy is transferred between particles in its intricate equations, which outline how photons are carried through the dense plasma. This enables us to compute how transparent the solar material is to radiation at varying temperatures and densities, and then we can figure out where the radiative zone stops and the next layer starts. It's one of my favorite things about math. It lets us investigate places that we can never travel, sort of like how quantum tunneling lets protons jump over the Coulomb barrier and generate the photons we are tracing here. As our photon nears the top edge of the radiative zone, it crosses the tachocline, a narrow transitional zone where the radiative zone transitions into the next zone, the convective zone. The tachocline is a zone of intense contrast, where the relative flatness of the radiative zone encounters the boiling, bubbling convective zone. The peculiar conditions in this very thin layer most likely plays a central role in the solar dynamo that creates the Sun's magnetic field. The tachocline is believed to twist and strengthen the magnetic field, sculpting the sunspots and solar flares that characterize the star's surface. Zooming through the thin tachocline, our photon ends up at the convective zone, stretching out from roughly 70% of the radius of the Sun to just below the surface that can be seen. The photosphere, the temperatures have fallen to under 2 million degrees Celsius. Now, the plasma of the Sun is no longer sufficiently dense in order to successfully transfer energy in the form of radiation. Instead, the plasma becomes unstable and starts to travel in huge convection currents, similar to boiling water in a kettle. Hot plasma ascends towards the surface in great cells known as granules. These granules, which are up to thousands of kilometers in diameter, rush upwards under the force of their buoyancy at hundreds of meters per second. Like a beach ball that you've forced below the water, rushing to the surface as it squirms from under you. The force required to move this volume of matter against the Sun's gravity is astonishing. Imagine the force of 10 billion hurricanes, and you'd be just starting to approach the energy generated in these fusion processes results from a tiny quantity of mass being transformed into energy, according to Einstein's now iconic equation, E = mc2. During the process of fusion, the mass of the formed helium-4 nucleus is just a bit smaller than the sum of the equivalent of the mass of 3 million cars being converted into pure energy each second. This is the energy that ultimately drives the Sun and gives it the light and heat that reaches the Earth. And before these photons, flowing out of these reactions, can reach the Earth and all the things else in the solar system and outside, they need to get out of the 700,000 kilometers turbulent solar interior above them first. To fully appreciate the complexity of the Sun and its layered structure, let's trace the path of a single photon, a light particle, from its formation in a proton-proton reaction all the way to the surface. This is anything. Travel begins in The core, an area that occupies approximately 25% of the radius of the Sun, but contains close to half of its overall mass. And as has also been told us, the core is extremely dense. Its density is at about 160 grams per cubic centimeter, making it more than 20 times denser than iron. To help one better understand, if your phone was constructed of material that dense, it would be as heavy as a sledgehammer. For our photon, what this means is that the environment is so densely full of particles that it can't travel very far before being absorbed by a surrounding particle. Naturally, not soon after, that particle will pack the photon's bags and send it out into the chaos of the core particle to catch and release in some arbitrary direction. It's a little like trying to push through a crowded room, where every so often, you bump into somebody and have to change course. This constant interaction of absorption and re-emission is what gives the core its nature, resulting in a journey for a photon that is more of a random walk than a direct path outward. This random movement of photons is reminiscent of Brownian motion, where particles suspended in a fluid move erratically due to collisions with smaller, fast-moving molecules. And there is no bias for the direction that a photon might fly back, out of a particle that had just absorbed it. In theory, a photon might travel all the way to the surface of the Sun before random chance sends it flying back toward the core. To make things more complex, as photons are constantly absorbed and re-emitted, the energy decreases slowly from gamma rays, X-rays, and finally to visible light as they travel towards the outer layers of the Sun. It has been a difficult task for astronomers to understand what goes on in the core of the Sun. The core is fully hidden by the outer layers of the Sun, meaning we can't see it directly with any form of illumination. Rather, scientists have created genius ways to deduce the dynamics of the raging fire below. One of the most important techniques is the examination of helioseismology, the observation of waves undulating on the Sun's surface. Just as seismologists examine earthquakes in order to learn about Earth's interior, measure the vibrations on the Sun's surface caused by sound waves that travel through it are also released during the fusion reactions in the Sun's core. Neutrinos interact so weakly with matter that they can travel straight out of the Sun in just 2 seconds, hardly aware of the tangle their photon counterparts are caught up in. For decades, solar neutrino detectors on Earth measured fewer neutrinos than predicted by theoretical models, leading to what was known as the solar neutrino problem. It wasn't until scientists discovered that neutrinos change their properties or flavors on their journey to Earth that the mystery was resolved, confirming both our understanding of particle physics and the nuclear processes in the Sun's core. Secondly, the photon reaches the radiative zone, which spans from the outer edge of the core to 70% of the Sun's radius. Temperatures here slowly decrease from 15 million degrees to approximately 2 million degrees Celsius, and with the decrease in temperature, the density of matter also decreases, from approximately the density of gold in the depths of the zone to less than water at the surface. The prevalent energy form of transportation remains this frantic process of photons bouncing off inside layer, transporting their energy on average towards the top. And as the plasma's density continues to fall away as we travel further out, our photon has a little more leeway, able to make larger jumps between interactions. But even here, beyond the core, the material of the Sun is still dense that even a few centimeters would be able to stop as much light as hundreds of meters of water. We are able to envision such precise models of the Sun's interior because of models like the Standard Solar Model or SSM. It is a mathematical framework based on the principles of hydrostatic equilibrium, energy conservation, and radiative transfer, essentially using our understanding of how materials and fluids behave here in our laboratories on Earth to infer the properties of a location beyond our reach. The SSM simulates how energy is transferred between equations, explaining how photons are carried through the dense plasma. This enables us to calculate how transparent the solar material is to radiation at various temperatures and densities, and we can then calculate from there where the radiative zone stops and the next layer starts. That is one of my favorite aspects of mathematics. It lets us investigate worlds that we can never go to, sort of like how quantum tunneling lets protons tunnel over the Coulomb barrier and generate the photons we are currently tracking. As our photon reaches the top edge of the radiative zone, it enters the tachocline, a thin transitional zone where the zone connects with the next zone, The convective zone. The tachocline is a zone of radical contrast. Zone comes up against the bubbling, boiling convective zone. The unusual conditions in this very narrow layer most likely plays a critical part in the solar dynamo responsible for the sun's magnetic field. The tachocline is believed to wind up and enhance the magnetic field. Molding the sunspots and zipping along the thin tachocline, our photon reaches the convective zone. Stretching out from roughly 70% of the radius of the sun to just below the surface, the photosphere, the temperatures have fallen to less than 2 million degrees Celsius. Now, the plasma of the sun is no longer dense enough to efficiently transfer energy by radiation. Rather, the plasma becomes unstable and starts moving in giant convection currents, similar to the boil on the surface of a kettle. Plasma that is hot flows up to the surface in huge cells known as granules. These granules, with diameters of thousands of kilometers, rush up under the energy of buoyancy at hundreds of get close to the energy necessary. This convective process moves energy much more efficiently than the radiative zone, creating turbulent, rolling waves of plasma that churn vigorously. This is a significant change in how energy is transported. While photons still interact with particles, the major mechanism for energy transfer in the convective zone is no longer the random reabsorption and re-emission between particles, radiative diffusion, but instead the motion of hot plasma rising and cooler plasma descending. Energy required. This convective process transports energy much more effectively than the radiative zone, producing turbulent, rolling waves of plasma that churn strongly. This is a dramatic shift in the way that energy is being transported. Although photons continue to interact with particles, the main method of energy transfer in the convective zone is no longer that random absorption and re-emission between the particles, which is radiative diffusion, and instead the motion of hot plasma moving upwards and cooler plasma moving downwards. This convective motion transports the energy outward more effectively than in the radiative zone. When it reaches the top of the convective zone, the photon is taken to the photosphere, the sun's visible surface. The temperatures have now cooled to around 5,500 degrees Celsius, and the plasma has thinned sufficiently so that photons may escape without continually being reabsorbed. It is from this narrow, approximately 500-kilometer thick layer on which the light we observe from the sun is radiated. Over them there is only the corona of the sun, which is itself an interesting environment, but only approximately a billionth of the density of the photosphere, and hence not a very great barrier to our photon. It is surprising that such a body as the sun, which many describe as a ball of gas, should possess such a definite boundary. But the photosphere is where our photon eventually breaks free, moving at the speed of light, and off it goes through the expanse of space, our neutrino companion that was formed at the same moment. It's well out of the Milky Way system by now, since, entering its steady main sequence stage, nuclear fusion has changed the sun's layers, slowly increasing its brightness over billions of years. This is due to the fact that the process of fusion naturally causes changes in the composition, density, and temperature of the core of the sun, and thus in the general behavior and the destiny of our star. As hydrogen fuses into helium, hydrogen gradually depletes in the core, and helium ash begins to build up. Unlike hydrogen, which readily undergoes fusion at the sun's current core temperatures, helium requires much higher temperatures to fuse. As the abundance of helium increases, the core becomes denser. Helium nuclei are more massive than hydrogen nuclei, and as more helium accumulates in the center, the general density increases. Meanwhile, since helium isn't fusing and generating energy, it isn't adding to the outward radiation pressure that balances the sun's huge gravitational pull. The effect is that gravity will start to dominate, forcing the core to shrink further. In order to avoid collapse due to its own gravity, the sun will need to raise its core temperature as helium accumulates. The warmer core cranks up the dial on hydrogen fusion, since nuclear fusion is incredibly sensitive to changes in temperature. This rise in fusion emits more energy, which leads to a brighter star and briefly returns the balance between gravity and radiation pressure. In this process, the sun's energy output has increased by approximately 30% throughout its lifetime, and will continue to do so for billions of years as long as hydrogen fusion remains the dominant process in the core. In the radiative zone, the layers have become hotter and more opaque. The temperature rising of the core results in more energetic photons being created, which have a higher probability of interacting with the plasma around them and bouncing around. Consequently, this region is now less efficient at radiating energy outward, holding photons for longer before they can resume their flight. The convective zone has also increased somewhat in size as time went on because of the greater energy production. As the Sun continues to burn through its hydrogen fuel, over the next 5 billion years, its core will eventually be left overburdened with inert helium that can no longer sustain fusion under its own pressure. When this happens, the Sun will evolve into a red giant, dramatically expanding and enveloping its inner planets, such as Mercury and Venus, and quite possibly, the Earth. During this stage, the core will shrink and become hotter until it ignites in a helium flash, initiating the fusion of helium into heavier elements such as carbon and oxygen, once again swinging the pendulum between the ineluctable gravitational pounding and resisting pressures of energy from the core. This process will build new layers and make the Sun swell yet more before ejecting its outer layers to create a ghostly remnant, a planetary nebula. The core that is left will cool and die, becoming a white dwarf, a dense, Earth-sized ember of a one-time raging fire. This video has no sponsor, but it's still possible due to all of you who support the channel on Patreon. As a thank you, we've been posting these stunning pictures of space as phone and computer screensavers. There's the Milky Way, Venus, and now, for today's video, the Sun. You can receive the screensavers when you sign up on Patreon, or you can purchase a printed version in our Displate store. Not only do you receive these gorgeous posters, but you will also be supporting our channel. Most of what happens inside the Sun is invisible to us, but its impact on our lives is no less insidious. And yet its presence on our lives is ubiquitous, breathtakingly so. If I were to tell you that the cycles of the Sun could affect your entire life, you might think that I was suddenly taking a turn away from astronomy and into astrology. While there are quite a number of individuals in the world who feel that you can learn about your future by examining the alignment of stars and planets, it's not a position I like to take on this channel. I'm more interested in the aesthetics of space and the mechanisms that make it so. But occasionally, there is truth in even the most unexpected tale. So let me don my prophesying hat. Although I'm no horoscope writer, I shall foretell that according to the present position of the Sun, this year in 2025 you may be more prone to ill health, less trustworthy technology, observe warmer conditions, with less cloud cover, and maybe might be affected in some other unexpected ways. Why do I say this? Because it seems the Sun, that big ball of flames in our sky, is not only the source of where we obtain our energy. Science is beginning to reveal that its 11-year cycles could well be the metronome marking out the way life on our world ticks. Tick, ticks. How can that be? Let me tell you. It is no wonder that the Sun has a major influence on life on Earth. Indeed, in many ways it is life's source. Life on Earth requires energy to function, and the Sun frequently provides that energy. Light for plants, plants for herbivores, herbivores for carnivores, all the way up the food chain. It's hard to find anything on Earth that could live without our Sun. But beyond the gift of that life-sustaining energy, it's simple to imagine the Sun as quite stationary. We observe it rise and set in the sky, but we don't often pay attention to it changing in any way. This is an illusion, though. The Sun changes continuously. We've already discussed much of this. The Sun is a seething, flowing body of barely contained plasma, which often isn't contained. Despite the strong gravitational force that keeps it intact, the nuclear reactions within its core are so fiery, attaining 15 million degrees C at its center, that plasma bubbles and erupts on its surface, bursting into solar flares blazing in every direction. Sunspots. Black spots on the Sun's surface that are occupied with strong magnetic fields and are 1/600 to 160,000 kilometers in diameter, occur, migrate, and disappear. Coronal mass ejections, CMEs, burst out of the Sun's corona, the region of atmosphere above the Sun that is mysteriously 200 times hotter than the Sun's surface. It's hard to find a place in the solar system that is as active as the Sun. What many people do not realize is that that activity waxes and wanes. The Sun operates on an 11-year cycle that alternates between a period of low activity, the solar minimum, to a much greater altitude, the solar maximum, and back once again. Sunspots, solar flares, and CMEs all occur more frequently during the solar maximum. You are 50 times more likely to observe a solar flare during solar maximum than during the Sun's minimum, and big CMEs go from occurring once every few days or even several times a day. This is referred to as the Schwabe cycle. Interestingly, this is one half of an extended cycle referred to as the Hale cycle, which charts the fluctuations in the Sun's magnetic polarity. Every 11 years, once in a Schwabe cycle, the Sun's magnetic North Pole and the South Pole change places. When there is another Schwabe cycle, the poles switch again. Tick, tick, tick. This perpetual rise and fall of levels of solar energy hums through our solar system, rising and falling like a heartbeat. And amazingly, although we can't see it, we on Earth shift to its beat. We don't actually know why the Sun goes through this cycle. It's obviously connected to the magnetic processes that exists within the Sun itself. Nevertheless, even though we have seen these cycles in operation for the past 200 years and have observed evidence of their effect on the Earth for the past 10,000, we're still no closer to understanding why the Sun's cycle takes that specific amount of time, not another. What is the force behind it? Having no other ready answer, some scientists have attempted to relate the orbital duration of Jupiter, roughly 11 years as well, to this cycle duration, but this may well be a fluke. Though Jupiter accounts for 2.5 times the total mass of all the solar system's planets, and certainly has some gravitational influence on the Sun, its own orbit does not account for the changes that the Sun's cycle does experience. A lot of the activity that occurs within the Sun is a mystery to us. But what effect it has on Earth? That is easier to observe. It starts with the space around us. Space becomes increasingly vital to modern civilization, so it should not be surprising that CMEs and solar storms flowing out of the Sun regularly would have an impact on the technology we have up there. Scientists are able to predict the arrival of a solar storm, known as a geomagnetic storm, by the time it arrives at Earth, days or even weeks in advance. This allows astronauts to go into safe shelters to hide themselves from dangerous increases in radiation levels, and it helps the sensitive hardware on satellites get shut down so that hardware won't get fried. That's significant, because solar radiation can induce unanticipated electrical currents in wiring, which will overload systems that have not entered a safe standby state. But there is another side to geomagnetic storms which you may not anticipate. All of that radiation affects the atmosphere itself. It heats it, even though just a bit. When the atmosphere heats up, it expands, and this affects our satellites. Outside of space, there is no drag, and so objects can orbit nearly indefinitely. Well, this isn't entirely true, and satellites in low Earth orbit do occasionally, about 4 times a year, need to expend fuel to correct their orbits, as there is still a tiny amount of atmosphere up there. But when a geomagnetic storm occurs, the atmosphere blossoms upwards, and LEO satellites have to maneuver every 2 to 3 weeks to avoid falling from the rapid friction. And this isn't always sufficient. In 1989, there had been a geomagnetic storm that had been so strong it knocked the NASA Solar Maximum mission out of the sky, as an increase in atmosphere suddenly brought the satellite down. Ironically, the mission had been observing solar flares. This is not a one-off occurrence. NORAD must reposition hundreds of satellites following every geomagnetic storm, as they have been removed from their previous orbits. Radiation also has an effect on our ionosphere, filling it with charged plasma. This can have a minimal lensing impact on our GPS technology, lowering its precision from within a meter to more than 10 meters. The following time you glance on Google Maps and it believes you could be a street away from where you are. A geomagnetic storm could be the culprit. Our power grids prepare themselves every 11 years for the increase in these current-causing events to avoid being overwhelmed. Amateur radio operators and pilots of passenger aircraft actually appreciate this phenomenon. They make use of these solidified atmospheric conditions by reflecting signals off of them like stones skipping across water, greatly extending their distance on high-frequency radio frequencies. Nevertheless, for all of those who are not ham radio enthusiasts, as I foretold in my horoscope, all this is topped off by some less reliable technology. The fact that the next solar maximum is already in progress, which makes me very confident in my prophecies. There are some positives to this. As space weather gets more agitated, regions of the globe like Canada experience an increase in the frequency of auroras, hypnotically dancing through the sky. Aurora chasers mention increases in sightings from several times a year to up to 2 times a month, along the most active phases of the Sun's 11-year cycle. So much for the Sun's power on space and our technology. You would think that that's it. The Sun's cycle may influence machines, but it's not going to have much impact on anything living, right? If you believe that, you'd be mistaken. It's not for nothing that the rest of my horoscope said poorer health. There's increasing evidence that the Sun's cycles can even affect ecosystems and species themselves, and that includes humans. Some of this is accidental. When the Schwabe cycle is at solar minimum, the Sun puts out less pressure via its solar winds, meaning ironically that we are less protected by our heliosphere from cosmic radiation. It's a highly energetic form of radiation, but luckily seldom manages to make it through our atmosphere for that very reason, since it's probably going to be absorbed or deflected by an air molecule passing by. But making it to the atmosphere is sufficient to create an effect. There's a theory, still far from certain, but that this additional radiation might be forming nucleation sites in the atmosphere that seed additional clouds, affecting our weather. Even helps if that's not happening. Around solar maximum, the space weather that strikes our atmosphere can produce a slight increase in global temperatures, as my horoscope forecasted. Warming of the weather. Not by much, it ought to be noted. Less than half a degree. And the temperature always, ultimately returns to its initial state. But it's sufficient that it's perceivable to species that are sensitive to temperature, such as to determine when to initiate the mating period. Research on birds has shown that on warmer years they tend to lay eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands went as far as to show that the laying times of blue tits were also affected by the number of sunspots occurring, which even the researchers found hard to explain. It's not as if birds can glance at the sun to observe how many sunspots there are. However, a correlation does appear to exist based on the 5 nesting groups which were examined. This isn't something that affects just blue tits, or even species like homing pigeons that are sensitive to magnetic fluctuations, who fly different routes, depending on what time in the 11-year cycle it is. I'm talking about the last unmentioned point in my horoscope: bad health. There are numerous studies on how solar cycles might influence us. In 2011, a study spanning 2 decades of nearly 1/3 of the women in Holland discovered a peak in 6 cervical pathologies that took place just after solar maximum, when the sun's radiation was hitting hardest. The same study also checked 1 man during the same period, which admittedly is a lot fewer candidates. Nevertheless, it was fascinating to consider that the man underwent mild increases in oral temperature, pulse rate, blood pressure, and respiration. Rate occurred shortly after solar maximum as well. It's not merely physiological. There is even an effect on the incidence of mental disorders. A 2006 study examined 237,000 clients in the main Medicaid database from 1995 through 2004. They determined that, out of all those clients, those who were born in more energetic, chaotic cycles suffered a higher incidence in mental disorders. If this is so, then the sun's cycle at the time of your birth may just have influenced the entire direction of your life. It's not exactly star signs, but astrology may just be on to something, at least with one particular star. Ultimately, the science about this is still in progress, and it must be emphasized that any effects on health brought about by these cycles are really very small. As one scientist said, it required hundreds of thousands of patients to even see that there was some effect on health. Sun cycles should not stop you from living your life. We're currently heading towards a solar maximum, predicted to arrive in 2025. But for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might also lead to a rise in creativity and adaptability. Perhaps it was in one such solar cycle 80,000 years ago when a human brain was initially mutated to provide it with abstract thought and consciousness. If so, if they provided us with the ability to see the universe, we owe a lot to solar maximums. We wouldn't exist without them. By this time, you may have gotten the impression that although there is a lot we have discovered about the sun, much more remains an unexpected enigma. For the brightest thing in our sky, the sun ironically remains in the dark with respect to many of the hows and whys of its mechanisms. But scientists are attempting right now to pierce the veil, and to do so, they are bringing to bear some impressive pieces of kit. Both NASA and ESA have sent spacecrafts to study the sun in the last decade. These missions are the closest we've ever been to our star, so close in fact that they are able to engage with its atmosphere directly. So why are we launching these spacecrafts to the sun? What will they be doing there? What have they discovered? And what makes each one of these missions unique and special? Let's start with NASA's effort, the Parker Solar Probe. The Parker Solar Probe was initiated in 2009 and launched on August 12, 2018, on a Delta IV Heavy rocket. It utilized 7 Venus flybys during almost 7 years to slowly reduce its orbit around the Sun. In the last month alone, on the 24th December 2024, it made its closest pass to the Sun, so close to the Sun's surface that the probe was mere 6.16 million kilometers away, within the Sun's corona or its atmosphere. Standing that close would be like having 500 suns in the sky radiating down at the same time, with temperatures as high as 1,400 degree, 2,500 degree. The spacecraft is moving 7 times closer to the Sun than any previous spacecraft has, and at such temperatures many of the components used to construct sensitive equipment for spacecraft would melt away. To keep the spacecraft and everything on it safe, it is covered by an 11-centimeter thick carbon composite shield, which can stand these extreme temperatures. This shield also consists of a white reflective coating that can assist in reducing heat intake. This shield will be constantly in the direction of the Sun, shielding the spacecraft in this extreme environment. Being away from Earth and orbiting a very deadly object, this vehicle is necessarily as independent as a spaceflight has yet been. Since the heat shield must always face the Sun, for most parts of its orbit, it will not be able to point its antenna toward Earth. During those periods of communications blackout, it will manage all of the sensors, manage data product formatting, and store high-resolution data, until it is able to contact Earth once more and relay back what it has recorded. ESA's Solar Orbiter mission started development in 2012, and 8 years later, the Solar Orbiter was launched on February 10, 2020, aboard an Atlas V rocket. The Solar Orbiter also employed gravity gets a helping hand from Venus and Earth, too. All these swing-bys place the Solar Orbiter into an initial 180-day orbit around the Sun. The spacecraft comes closest to the Sun every 6 months, at about 43 million kilometers away. This is relatively much farther away than the Parker probe's nearest approximations, but just to give you an idea of the temperatures at this distance still, at 43 million kilometers from the Sun, the temperatures can reach as high as 500 degrees, 932 degrees, as the sunlight will be 13 times more intense than what we experience on Earth. The solar orbiter is shielded by a heat shield made with titanium foil layers about 40 cm thick, which is not effective as the Parker probe's heat shield, but still enough to protect the spacecraft on its dangerous mission. The objectives of the Parker Solar Probe and the Solar Orbiter are similar to a great extent. Both these missions seek to learn more about our Sun's corona, its solar winds, coronal mass ejections, the magnetic field structure of the Sun, and just how it all works. The amount of particles ejected by the Sun is not fixed. Reconnection events in the Sun's magnetic field is able to unleash vast quantities of energy in the corona, expelling millions of tons of charged particles into space, in a single massive eruption. As already mentioned, this is referred to as a coronal mass ejection, or a CME. When these CMEs encounter the Earth's magnetosphere, it causes what's called a geomagnetic storm, and the biggest of these storms can be devastating. How devastating? To answer that, we'd need to look at the largest such event to ever impact the Earth, the Carrington event. From the 28th August to 2nd September 1859, numerous sunspots on the Sun in one location. On the 29th August, there were southern auroras seen as far north as Queensland, Australia, which suggests a solar storm was underway. Before midday on the 1st September, amateur astronomers Richard Carrington, after whom the event took its name, and Richard Hodgson independently viewed and recorded an extremely bright solar flare. Carrington and Hodgson reported in his own words, which were later published in scientific journals. The flare was part of a large coronal mass ejection that moved directly toward Earth and took 17.6 hours to cover the 150 million kilometer distance, considerably quicker than the velocity of typical CMEs. CMEs usually take a few days to arrive on Earth. It is believed that the speed at such a high level in this CME was facilitated by a previous CME, perhaps the origin of the giant aurora event on the 29th August, which removed any ambient solar wind plasma for the Carrington event, such as a massive slipstream. With slipstream established, the path was clear for the largest CME known to man. On 1st or 2nd September 1859, the largest ever recorded geomagnetic storm took place. Auroras were observed throughout the world, from all over the northern hemisphere to as far south as the Caribbean. The aurorae in the Rocky Mountains of the U.S. were so intense that the green glow awakened local gold miners, who started preparing breakfast because they thought that it was morning. It was noted that due to the brilliance of the aurora, individuals in the northeastern United States were still able to read a newspaper. The aurora could be seen as far from the poles as sub-Saharan Africa, Monterey and Tampico in Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes very near the equator, like in Colombia. This is unprecedented because, normally, aurorae aren't visible at middle latitudes. By the 3rd of September, the aurora in the sky was described as the brightest and most brilliant it had ever been. However, though lovely, this storm also caused unexpected issues. A side effect of the geomagnetic storm was the electrically charged particles from the Sun overran telegraph systems throughout Europe and North America, that resulted in them breaking down, even in some instances giving electric shocks to the people that worked the telegraph apparatus. Telegraph pylons generated sparks from the charged air. Amazingly, some telegraph operators could still continue to send and receive messages even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb, fairly harmless to humans, but extremely bad for electronics. The force of the CME in 1859 was so powerful that it squeezed the magnetic field of Earth all the way down into its atmosphere. Because North America and Europe were in the direction of the Sun at the time, these regions of the world were most hit from the first cannonball of the CME. Reminiscing about geomagnetic storms since the 1850s, there have been a few that were large, but not catastrophic. For instance, in March 1989, a CME struck Earth, making satellites unavailable for a Few hours and making radio stations in Europe jammed. Quebec power was shut down for roughly a day. Some of the population there mistakenly believed the Soviets were invading, and the glow in the air was due to nuclear bombs. Luckily, however, this solar storm and several similar to it did not cause any lasting harm. Nowadays, if a CME of the magnitude of the Carrington event or larger were to strike Earth, the effects would be much worse than they were for humankind during the 1800s. Technology was only barely starting back then, while now we have satellites, orbiting in space, computers, telecommunications, power plants, and others that all would be badly harmed in such a disaster. Because of the scope of a solar storm, it would significantly affect machinery over the power grid, and telecommunication, which have wires laid out over a great distance. Without the right protection there, transformers on the electrical power grid would fail, and millions would be left without electricity for an extended amount of time. If transformers were damaged, for instance, it would take years to replace, since transformers take years to produce. These transformers are very often custom designed for the specific need and are not produced in large quantities. Refrigerators would not be able to prevent food from perishing without power, and since the transport network would also be inoperable, since fuel pumps need electricity to operate, that food would have to be troublesome. Payment systems based on credit cards would not function. Individuals would not have access to the internet, since computers would lack power, and battery-powered equipment would drain quickly. Radio and television stations would be interrupted. Hospitals would face difficulties when the backup generators are out of fuel. We would be totally isolated from the rest of world. World is just so reliant on technology and particularly on electricity. It is feared we have lost the capacity to operate as a society in the absence of it. Just consider the response when TikTok went offline in America recently. And alarmingly, it is our power grid that is most at risk of a supersolar storm. A self-styled think tank has recently estimated the cost of damage to the USA alone at $2.6 trillion, effectively ruining the economy. Unfortunately, that doesn't tally the social consequences it might have. As usual with natural disasters, there will certainly be individuals who will fall back on more primitive instincts with mindsets such as every man for himself. Confusion, looting, and disdain for the law might happen. This would only worsen as time went on the longer the population remains in the dark from their government or organization of power. Hopefully, in type of situation, the betterment of mankind would emerge, but it is a likely possibility. The think tank put the estimated recovery period to fix the damage of the CME at 4 to 10 years, and estimated that 2/3 of the U.S. population may starve, get sick, and die in chaos within this period. This may sound a bit grim, but when it comes to the sun, it is better to know the risks than hope they aren't there. Unfortunately, CME flares are quick. They have been proven to arrive on Earth in only 17 hours. This may not be sufficient time to alert the whole population, switch off reactors, and take adequate precautions. In the real world, we have simply been fortunate so far, as we narrowly avoided a Carrington-sized event impacting us by 9 days, back in July of 2012. 9 days later, and Earth would have been slightly more advanced in its orbit and in the path of the CME, which is why it's crucial for us as a fragile species to know about the sun's corona, so we can be able to better anticipate solar storms, to provide us with improved warning and hopefully prevent damages related with a Carrington-sized event actually occurring us. It's just a question of when and not if. These two probes might sound the same, and although most of their objectives do overlap, they both share some distinct characteristics. The Parker probe is venturing deep into the sun's corona, where no man-made vehicle has ever ventured before. Due to the fact that it needs to endure temperatures so high, the spacecraft is not able to do a lot of things. For instance, it is not able to take any photographs of the sun, since there was no existing camera technology that could look directly at the sun from so close and live. But the Parker probe is equipped with devices that can sample and directly collect information regarding the particles that are present in the sun's corona, and even study closely where solar winds are generated, something that can't be done at a distance. The Parker probe is lighter, smaller, and has less equipment when compared to the solar orbiter. The solar orbiter, on the other hand, carries both particle detectors and telescopes. It can take close-up pictures of fascinating solar landscapes, and due to its orbit, it is able to track a region of the solar atmosphere for much longer than is possible from Earth. This enables it to observe storms building up in the atmosphere over several days. So, as you can see, these probes are complementary, and both will contribute to our knowledge of the sun's corona in their own manner. So what have these missions done so far then? Well, as noted, on 24th December 2024, the Parker probe flew by within 6.16 million kilometers of our star, closer than any spacecraft has come before, and it also became the fastest traveling human-made object to have ever traveled at 692,000 km on its death-defying plunge. The information received from the Parker probe is already informing our knowledge of how the magnetic field of the sun and the corona interact to create solar winds. They also found that magnetic fields from the sun sweep through the solar atmosphere, which can accelerate the solar wind speeds by up to 500,000 km/h. In addition, it has found proof of a dust-free zone 5.6 million kilometers from the sun. It's thought that this is caused by the vaporization of cosmic dust particles through the radiation from the sun. The solar orbiter has already returned its first images of the sun, and scientists discovered something termed campfires, which you can see here. These are explosions on the surface of the sun that happen due to fluctuations in small magnetic fields. The solar orbiter also captured the closest images ever of the surface of the sun from 77 million kilometers away, and the study of particles throughout its orbit will enable us to learn about various types of space weather. But maybe the most amazing discovery that these probes made was not what they observed coming from our sun, but what they listened to, which poses the question, what does the sun actually sound like? It's a straightforward enough question, and one that has a straightforward enough answer. The sun is quiet, of course. Since sound doesn't propagate through a vacuum, to us the sun makes no sound at all. But let's do away with easy answers. What if sound truly could travel through space? Without a giant cosmic muffler between us and our nearest star, what would we hear? Would the sun sing to us, an alluring tune in our heavens, or would its sound be so catastrophic a din it would immediately be the very last thing we would ever hear? Scientists do have the answer. By means of spacecraft such as the Parker probe, which is presently performing skimming orbits around the sun, they can determine the types of pressure waves and particles emitted by the sun, and can transform such waves into the sounds we would potentially hear if space were able to carry such propagation. And a fascinating thing to note, not everything that the sun sounds like is identical, and the sounds could enable scientists to figure out two of the sun's biggest secrets. In our fictional situation where space has suddenly acquired the capacity to carry sound, we can now begin hearing the sun all the way from the Earth. Though the Earth is 152 million kilometers away from the sun on average, it's not really surprising to discover that the sun is extremely loud, audible from where we stand. It would be something like this. Just a reminder, there isn't any sound in space. This is a sound reconstruction, converting amplitudes and frequencies into sound waves, making recordings of what the waves would sound like to the human ear if they were surrounded by an atmosphere. It has this very calming buzz that feels almost electrical in nature. It is reminiscent of generators, or even something dimly radioactive, which is fitting, since this is the sun we're talking about. The nuclear fusion going on inside the sun is equal to 3.85 s226 W every second, about 1 million times more than what humanity produces in an entire year. All of this power being created has an unsurprising knock-on effect on the volume of the sound the sun would produce. To get a sense of what this would be like, take device that you're watching this on and connect it up to the speakers they use at your next rock concert. Now play this sound at maximum volume. At 110 dB, it is safe to survive for brief periods of time, but would probably leave the whole population of the world going deaf if they weren't wearing earplugs as it sounds in our sky constantly. In fact, we can look upon it as very lucky that we don't really have to contend with this. Species would have likely developed with no ears because hearing would be useless. When we approach closer to the surface of the sun, that level of sound increases exponentially, with some grading it at 270 dB. Don't forget, decibels are a logarithmic unit, so for every 10 dB it increases. You must multiply the sound level by 10. For an idea of how loud this would be, 270 dB is more than our atmosphere itself can physically transmit. There is a limit to sound at 190 dB in Earth's atmosphere, as different media have varying volume limits, because of some complex idiosyncrasies of wave amplitude and energy levels, which we need not explore here. The volume of the sun would be 100,000 times greater than this limit. The sun is very loud, which is a pity, because some of the sounds of the sun can only be distinguished when we penetrate that ear-shattering area. At the time sound of the sun has arrived at our doorstep, most of the sun's sounds have merged into one, i.e., we lose some of their interesting infinities. In order to get a better perspective on the sun, we would have to move in closer into that deafeningly loud area of sound. So let's overlook the loudness of the sun for the time being, and let's rather concentrate on its sound sequences. If we were to board a spacecraft and travel toward the sun, we would shortly start to notice a difference in the uniformity of the sound. Instead of constant buzzing, what we would be hearing is something like this. This is the solar wind sound. The sun sends out a constant flow of charged particles blasting out throughout the solar system, and its presence accounts for one of the sun's greatest mysteries to have been posed so far. You see, it's natural to imagine this stream from originating within the sun and shooting out into space under the awesome power of all that nuclear fusion. But by the 1960s, a significant discovery had been made through observation. Whilst particles within the sun's atmosphere, or corona, were moving at an average rate of 145 km/s, particles outside of the corona were moving at 618 km/s. That meant particles that had enough velocity to escape the sun's surface were floating into space, and then something within the sun's corona was hyper-accelerating them from subsonic to supersonic velocities, shooting them off. What sort of process or mechanism is responsible is still a mystery to this day. The corona has a second mystery as well. It is much too hot. While you might think the center of the sun would be the hottest part of it, and the temperature would slowly decrease the further from the center you travel, this no longer holds true once you pass into the corona. The surface of the sun has a mean temperature of 5,500 degrees C, but only a few kilometers away, the corona makes a sudden temperature rise to as much as 2 million degrees. There is something in the sun's corona that is spraying solar wind into space, and something that is making things extremely hot. Scientists do not know why this is occurring either, though it is believed to be related to magnetic fields. It's here that we would encounter the third sound of our sun tour. As our spaceship approached nearer, and we flew over the dividing line between the corona and space, something also referred to as the Alfvén's surface, we would start to hear the following. They are referred to as Langmuir waves. They are created by small vibrations of plasma particles shaken by light itself as it flows from the sun through small funnels on the surface of the sun. A magnetic counterpart of the noise a kettle emits when it boils. We have entered one such stream. Millions of such streams shoot out from the sun's surface. The sun's outer surface is smothered in islands of hot stuff rising from the center of the star. The granules we've already discussed. Once there, the material condenses and falls back into the star's mass along the edges of the granule, And something involving this process of falling and rising material, or something occurring inside the sun itself, causes these falling zones run out intense magnetic field lines. Plasma is drawn up by the magnetic force and off it goes streaming into space, the origin of the solar wind. Scientists don't know what creates this process, but the sound of Langmuir waves is hauntingly lovely. As the winds depart, not all of the waves generated in this manner move at the same speed. This serves to spread out sounds as faster sections of the wave get ahead, while slower portions of the wave lag behind, producing what are referred to as dispersive waves. These waves are full of chirps, tiny whirlpools of sound, where fast waves arriving from the rear intercept slow waves that are already heading ahead. Eventually, this balances out into the hum we listened to at the start. There is one final sound that could provide an insight into the whole enigma, one that has some interesting implications. Here, right in the middle of the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high-energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth. Whenever lightning cracks, you get more than just thunder. A ripple travels through the planet's magnetosphere that can be picked up kilometers away, if you have the right detectors. To really get a feel for the magnitude of these waves, here is what they're like on Earth. Just a few little tiny cracks and whistles. Nothing at all special. Now here's what they sound like on the sun. To progress from sparse fleeting clicks to a cacophony of wailing wind shows that the sun's magnetosphere is not merely undergoing the intermittent crack of lightning. Something is happening continually, everywhere, combining discrete moments into one continuous roar. Scientists are still attempting to determine what that roaring is being brought about. But at least one theory for the power behind this sound, which can explain for the dramatic speeding up and superheating of matter in the corona, is a dry, sounding small thing known as magnetic reconnection. Magnetic reconnection has a pretty benign sound, and yet its benign, technical-sounding name conceals a disaster. The sun is a vastly coiled ball of changing magnetic field lines, all thanks to that turbulent plasma inside its heart. I cannot emphasize sufficiently how strong these are. When magnetic field lines move away from the sun, it is sometimes possible for them to cross other field lines, resulting in some of those classic loops forming that you've probably seen in pictures of the sun previously. But when such arcs are created at any given time, everything goes haywire. When two parallel lines intersect, forming an arc, there is a huge realignment in the polarity of excess field lines. All that lies above the arc must find somewhere to go to, so magnetic equilibrium is preserved. Cut off their tethers, the field lines further out from the sun create an arc of their own, which then shoots off into space like the release of a gigantic stretched-out rubber band. This very quickly speeding up magnetic force is called a nanoflare, and it heats the corona above it indirectly to multi-millions of degrees in seconds. Scientists only recently gained the ability to be able to even observe nanoflares, and aren't completely sure the nanoflares they've observed are actually the hypothesized events they were anticipating, though they do appear to be accompanied by the anticipated superheating. This is still an explanation that is being developed. Most of it remains a mystery. And yet, it isn't entirely out of the question that such episodes, when the sun gets so agitated, it snaps account for why its corona is so hot, and why it is hurling solar winds out into the solar system with rather the intensity we hear. While, to go from one crack to the deafening wail we can hear, and to explain the ongoing solar wind moving outwards in all directions, the sun, nanoflares, or whatever power is behind this effect, will be very widespread throughout the entire corona. The sun continues to hold many mysteries. The Parker Solar Probe, which collected many of these sounds, continues its journey around the sun, gathering valuable data with every pass. The Parker Probe is nearly at the end of its 7-year mission, but hopefully it will collect plenty more information for scientists to study. Maybe they will have additional sounds for us, with each one a clue to the mystery of how the universe functions. Because, ironically, just like listening from the seconds passing to the tick of a clock to attempt and determine how the clockwork works, the mysteries of the sun could one day be unraveled by what we listen to, and not by what we observe. You may assume that if we can send probes such as the Parker probe into orbit around our sun, then it ought to be simple enough to deliver other stuff to our sun as well. Have you ever considered whether the sun could be a solution to Earth's disposal issues? Earth has a pollution issue. There are plastics and waste from landfills, the kinds of things you would dispose of at home. And then there's hazardous industrial waste such as nuclear byproducts, biohazards, chemical toxins. These inhibit ecosystems and impact the health of vulnerable populations around the globe. The best we've been able to come up with so far for getting rid of nuclear waste is to bury it deep underground. Not optimal, considering that the stuff is still radioactive for tens of thousands of years. So why don't we just strap it to a rocket, blow it into the sun, like firing a missile at a target? Wouldn't that solve all our problems? This was a question asked of us by members of our community on Patreon, and its answer is not as easy as you'd imagine. To start responding to our question, it's really difficult to crash anything into the sun. Let's take a closer look. Let's say we've collected together a huge stack of toxic waste headed for the sun. The first thing we'd have to determine is how to put it in space. No big deal, right? We've been launching things into space for the better half of a century. To get our trash pack through the atmosphere and out past Earth's orbit, we'd need to accelerate it to a velocity of 11.2 kilometers per second. This is the speed known as the escape velocity, where the kinetic energy of the payload surpasses Earth's gravitational potential energy. Once free of Earth's orbit, our garbage craft is on course for solar collision, right? Wrong. Once our package escapes Earth's orbit, it's still gravitationally bound to the sun. Put super simply, Earth and everything on it is moving sideways relative to the sun at 30 kilometers per second. Combining this sideways movement with the gravitational force of the sun is what keeps us trapped in an orbit. If the sun were to somehow lose its gravitational force, we'd zip right past it at 30 kilometers per second and continue on. If we here on Earth were to lose our sideways motion, we'd be affected by the gravity of the sun and plummet straight into it. So there's hope for our trash ball, yet how do we lose our sideways movement to facilitate this solar free fall? Well, there's two possibilities. The first is to pull out enough fuel to brake in space. Now, technically speaking, you can't actually brake in the space vacuum. But the next best alternative would be to set up our trash payload's thrust system to produce thrust opposite to its direction of 18 sideways motion. This eliminates the sideways motion, decelerating the spacecraft and allowing the sun's gravity to take over. Earth is moving around the sun at 30 km/s. So to brake a trash rocket fired from Earth, you'd have to be able to accelerate 30 km/s in the opposite direction of travel. Here's where it gets strange. The closer you are to the sun, the more difficult it is to crash into it. Let me clarify. The closer you are to the sun, the faster your orbital velocity. Mercury orbits at a dizzying 48 km/s, while Pluto cruises at a cool 4.7 km/s. The faster your orbital velocity, the more you'll need to decelerate to free fall into the sun. That's why it is actually much more fuel efficient to fly to the outer solar system, decelerate, and free fall into the sun from there. It's not inconceivable to accelerate a spacecraft 30 kilometers, as mentioned. NASA's Parker Solar Probe accelerated well beyond that, making it the fastest man-made spacecraft ever. But this brings us back to the problem of fuel. To make this brake and fall method work, you'd first have to launch your garbage payload into orbit around Earth, then shoot the fuel for the trip into orbit. After both halves are orbiting Earth, you can fuel your cargo and propel it beyond Earth's orbit and into orbit around the sun. Then, you'd need to burn the remaining fuel to slow down so it free falls into the sun. Why not fire both payload and fuel simultaneously? I ask. You? The catch is, it's just too much fuel. To give you an idea, the Saturn V rocket that took man to the moon required 2 million liters of fuel just to escape Earth's orbit. At 11.2 km SA journey such as this, would need orders of magnitude more fuel. No contemporary rocket technology would even be capable of being able to transport the amount required for a trip such as this. Alright, so scenario 1 is eliminated. What other alternatives do we have? Another method for slowing down in space is with a gravity assist. Typically, when we speak of gravity assists, we're referring to the type that slung the Voyager probes into the outer solar system. But gravity assists aren't utilized only to accelerate probes. They can be utilized to decelerate them too. If you were to approach a planet from behind, fly in front of it, and exit behind the planet like this, your spacecraft loses energy while the planet gains energy. The Messenger and Bepi-Colombo probes have both successfully used this gravitational assist technique to lose velocity and enter orbit around Mercury. The thing is, this takes a lot of time. Bepi-Colombo launched in 2018 and will only reach orbit around Mercury in 2025. Amazingly, its journey to get there is longer than Earth to Pluto. That's because to slow down enough, one gravity assist isn't enough. Indeed, Bepi-Colombo requires 9 different gravity assists to slow down enough to orbit Mercury. In the same way, slamming our trash into the sun is all a matter of precisely orchestrated orbital physics. A launch failure or explosion could be disastrous to say the least. Even the world's most successful rocket, the Soyuz, has a 2 to 3% failure rate. I don't know if you feel the same, but when nuclear waste is involved, I don't enjoy those chances. Even when the launch is successful, the project itself would be totally outrageous in cost. So outrageous that no rational individual would sanction the budget. There are way too many other missions on the table that would contribute so much more to science and to mankind than a garbage disposal mission. 10 and finally, it would be simpler, faster, and less expensive, but still outrageously expensive, to fire our trash out of the solar system into interstellar space. It would be less fuel-driven, as the acceleration one needs to get away from the sun's gravity is 42.1 km/s, a super close 12.1 km acceleration from Earth's orbital velocity. There you have it. We don't fire trash into the sun because it's really tough, super dangerous, and super costly. We're likely better off being more aware of what we use and how we recycle it. The sun is a mind-boggling component of our solar system, a vital component of life here on Earth. I hope the next sunrise you see becomes that little bit more special. I hope the pink and orange photons, scattering for one final time on the molecules of Earth's atmosphere, before streaming through your pupils will make you think of the incredible voyage they have endured, beginning with the collapse of a colossal cosmic cloud into an element building furnace, fighting for hundreds of thousands of years through a plasma melting pot to give you this lovely view. I hope that this journey has encouraged you to appreciate that everyday miracle we tend to take for granted. Please consider giving the video a like and merge with your thoughts down in the comments area. Thanks for watching.